Okay, so this is our last video of polynomials, which is nice. So this is a nice quick unit. This one we're focusing on solving polynomial problems. So this one we're going to have to make a couple of our own equations. We're going to look at that regression function on our calculator again, where if we plot like data points, it'll fit a line through it, that kind of stuff. So otherwise, it's really similar to what we've been doing. We just have to kind of come up with a couple of instances, or come up with equations, in a couple instances. So some helpful hints: we always want to identify two variables and state what they represent, right? So y is equal to an x squared minus 6x minus 12 or something. X and y both mean something, okay? So a lot of the time it's like time and height, or I don't know, one we're going to look at like the dimension of a box and volume, those sorts of things. So we need to figure out what those variables mean. That's important. We need to write the polynomial equation that models the problem. Sometimes easier said than done, but we can do it. We're going to solve for the unknowns and then state our answer in the context of the problem. So solving for the unknowns can often be done graphically. That's generally how we're going to do it. Okay, so example 1, given the following information on the flight of a golf ball, we're going to sketch a rough graph to represent the data, and then we're going to use our calculator to find the equation that models the data. So if I had to sketch like a rough graph, it's going, as time goes on, it's going up, and then it reaches kind of this maximum point, and then it starts going back down. So my like general path of this golf ball would look like that, where this is time and this is height. Okay, so we know that that's a quadratic function. And I know some of you guys took physics 20, so this should look familiar with a path of some sort of moving object that gets thrown up or hit up or whatever, and then gravity starts pulling it back down towards the earth. Okay, so because we're going to use our regression function in our calculator, I'm going to go back through the steps that we do to get that. Okay, so the first thing that we want to do is turn on our stat plot, we call it. Okay, so normally if I hit graph right now, I'm just gonna, this is some lines for later. There's no data points, there's the lines that I have in y equals, okay? When I want to use a regression, we need to actually be able to plot these points as like individual bits that then our calculator will draw this line for. Okay, so to do that, we want to press second button, and then we want to press stat plot, which is basically the y equals button. So we go, get out of that, we go second, stat plot. We're going to go into number 1 and turn it on. Okay, so we're going to go into 1 and then turn it on. Okay, so we just click on the highlighted on, and now we can see that it's on, and we can get out of that. Okay, then to put actual data in, then we need to hit the stat button. So stat is right below delete, so kind of right on the left there, so stat, and we're gonna go edit, so number 1 for edit, and then it gives us our list. So this is where we have previous data. I've done this already because I just wanted to see what it was, what it was gonna work out to. So we need to clear the data first. So we need to clear the lists because generally we won't have cleared them before. So what we're gonna do is we're gonna press clear on like L1 and L2. So I'm gonna scroll up, so it would default to there. I'm gonna scroll up to L2, I'm gonna go clear, and so see how it goes away there, and then I'm gonna hit enter. Same deal there, clear, enter, all my lists are empty. Okay, then I'm gonna enter my data. Okay, so at this point, I'm plugging these numbers in. So 0, 0.5, 1, 2, 2.5, 3, 3.5, 4, 5, 6, 6.5. And then 0, 18, 30, 42, 48, 49, 52, 50, 38, 14, 3. And remember how we talked about last time that we want the same amount of data points. If we were off by 1, we would have to go back and basically re-enter everything. Okay, so what that's going to do is it's going to give us actual points. I'm going to go play with my window. I'm also going to go clear my y equals so we're not like confused by what other lines are in here. And I'm going to go set my window to fit this data. So I'm going to go from an x minimum of -1 to 10 scaled by 1. And then I'm going to go from a y minimum, I'm just going to go -5 so we can see a little bit below, even though all of these numbers are positive. And then y max, it needs to go at least to 52, so I'll go to 60, we'll go by 10. Okay, so there is my kind of plot, and we can see that shape that we drew out. Now we need to tell our calculator to actually give us a function, give us an equation for this. So now we press that stat button again, and we go calculate. So we scroll over once to calc. And then this is when we need to pick the type of regression. So last time we did this, we were doing an exponential regression because we were dealing with exponential functions. Now we need to decide, do we want a quadratic regression? Do we want a cubic regression? And we already kind of talked about how this is a quadratic function. It's a parabola. So we're going to use number 5 in this situation to give us a quadratic regression. Okay, and then we're just going to hit enter, and look, it spits out an equation for us. So it tells us it's in the form ax squared plus bx plus c. That's a quadratic function. And then it tells us a, b, and c. I'm just going to round everything to the nearest hundredth. So y is equal to -4.66x squared plus 30.28x plus 2.05 is my equation. Okay, so if we go and put that actually into y equals now, and hit graph, see how we have a nice line that kind of flows through all of those points? Okay, what we're going to do is figure out the maximum height of the ball. So to do that, we're going to use second calc and use this maximum feature, so 4 that we went over yesterday. And we want that maximum part of the parabola, so it asks for a left boundary, so we need to go to the left. And then it asks for a right boundary, and then a guess can be anywhere. My maximum, it asks me kind of 2 parts here. So max height of the ball. So max height is going to be 51.24 when I round it. And it told me that that's in meters. So that's my max height. And then when this occurred is my x coordinate, right? We decided this was time. So 3.25 seconds when we round. Okay. So this is a little weird that this one's 51 and there's a point that's 52. What that means is the calculator just drew its best line. And so if you actually realize that and said 52 meters is the highest based on the data, I would give you either. I will try and make that not happen in a test, but sometimes stuff happens like it did now, okay? So sometimes the line of best fit is not completely 100% accurate, but it did a pretty good job, right? It went pretty well through all of those points. When did the ball hit the ground? So this time we're going second calc. If you want to write down second calc maximum, just so you remember if you want to look back for quizzes or whatever. Second calc 0 is going to give us, remember that's our x-intercept, and that is the point. And if I clear that, that is the point that I'm looking for, right? Where it hit the ground, how long that took is going to be my x-coordinate of my x-intercept. So I go second calc 0. And this is why I gave myself a little bit below that x-axis. My y region goes below into the negatives so that I can actually get down into the negatives. And my 0 is 6.56 seconds. So t is equal to 6.56 seconds. And I like to write SEC just because S's sometimes look like 5s, but usually I figure it out. Okay, so there's a calculator regression one. If I ask you guys to do this, it will be on the quiz when you can refer back to this because I don't expect you to memorize it. But I'm going to tell you right now that you will see something like this on the quiz, but just not on the unit test when you're not open book. Okay, another application is the volume of a rectangular prism is 6,000 centimeters cubed. Its width is 2 centimeters longer than its height, and its length is twice the length of the width. Okay, so we're going to write an equation to represent the volume V as a function of h, height, for the rectangular prism. Okay, so we know that these are going to be our two variables, right? So V is equal to h times something times something times something. We know that volume is equal to width times length times height, right? But right now we have 3 different variables and we can only ever have one, right? We've only ever dealt with like just x's or just t's or whatever. So what we need to figure out is the height, the width, and the length all in terms of one variable, and the variable that we're going to use is h. So height is just height. Then we need to go back into the question and say, okay, its width is 2 centimeters longer than its height. So if we say width is h plus 2, that means that it's 2 centimeters more than whatever the height is. And then the length is twice its width. So it's going to be 2 times h plus 2. So we could write that as 2h plus 4 if we wanted. Okay, now we can rewrite this just in terms of that one variable. So w is h plus 2. L is 2h plus 4, and then h is just h. So see how now we've got h times h, or 2h times h again. This would give us 2h cubed as that leading coefficient. Okay, so this is a cubic function, which makes sense because we're dealing with centimeters cubed, right? There's 3 different dimensions multiplying, and each of them includes that variable. Okay, so there's our equation. V is equal to that. And it doesn't say to multiply it out, so we can just leave it. What we're going to do is we're going to determine the height of the rectangular prism. What are the corresponding width and length of each? Okay, so it told me that volume was equal to 6,000. So if I replace my V with 6,000, then what I have now is I can graph this as y1 and this as y2, or vice versa, and actually figure out what height value is going to make this true, what value for h is going to make this true, which is that height that it's looking for in the question. So I'm going to graph y1 as 6,000. I'm going to graph y2 as x plus 2. I'm going to use x's instead of h's because they're just the easiest button to push, plus 4, and then x. And before I even hit graph, I mean I can hit graph, but it like goes like way out of the screen really, really quickly. And I've got a line up at 6,000, a horizontal line up at 6,000. So I definitely need to adjust my window. I'm also, because I'm seeing that I still have my stat plot on, I'm going to turn that off. So I'm going to go second stat plot, go into number 1, turn it off. So now if I graphed it, those would be gone. I've just got that line. Now I need to go play with my window. So I don't really know what my x min and x max need to be. But I definitely know that my y maximum needs to go up past 6,000, and I'm going to scale it by, let's just say 1,000. Okay, so now that just shows me that I need to go farther this way to be able to see where they intersect. So I need to go back in, and maybe let's change that to 50 and scale it by 10. And now we have a point where those two things interact. So this is the volume. As height gets bigger and bigger and bigger and bigger, that volume is increasing exponentially, and at some point that's going to connect and give me that volume of 6,000. So we go second, calc, intersect. So second, calc, intersect, and we get first curve, second curve, guess, perfect. Intersection, x is equal to 13.121. I'm going to keep 3 decimal places just to show you guys something at the end. Hopefully it'll be a little bit more accurate than when I did it with 2. So what this tells me is that x, or which is equal to height in our world, is equal to 13.121. That would be centimeters. Okay, so what that means is that if height is 13.121 centimeters, then width is going to be this plus 2, so 15.121 centimeters. Then length is going to be double that guy. Remember, the length is double my width, so it's going to be 2 times the 15.121, which gives me 2 times 15.121, just going to give me 30.242. Okay, so that's the width, height, and length of this thing. So that's part of what it, so that's like what it asked me. And then if we're unsure about that, we can just go, we can actually multiply all these out. So 13.121 times 15.121 times 30.242, we get basically 6,000 on the nose. And the reason why it's not exactly 6,000 is those rounding issues. Okay, so the more decimal places you keep, the more accurate it's going to be. But if you would rounded this to the nearest hundredth, you would have got like 5,998.8 or something, which is also very close. Okay, so don't feel like you have to keep more than like 2 or 3. Okay, so there's that question. And then our last question is should look really familiar. So a student throws a ball in the air from the top of the building. The height h in meters of the ball after t seconds is given by the equation this. Okay, so what this means, this is a squared, so it would look something like this. So my y-intercept would be at 20. It would go up, and then it would go back down and eventually hit the ground. Okay, so graph the path of the ball. We're just going to do that in our calculators. So I've got negative 4.9x squared, and again I'm using x instead of t, plus 32x plus 20. And because of my window from the last one, you can barely see that. Holy smokes. So we're going to go back into our window. I know that my y needs to go to at least 20, and it's probably going to go up from there. So I'm going to go y max of like 50, scale it by 10. And then x, we probably only need to go to 10, but we can see from there. Okay, so my x was accurate, but my y wasn't high enough still. This person threw it very, very high. So let's see if like 80 works. Voila, it does. Okay, so there's the path of my ball, and a person threw it very high. Okay, so what's the maximum height the ball reaches? We're gonna go, so we put y1, actually I put it as y2, but it doesn't really matter. We're gonna go second calc maximum. So second calc maximum. Left boundary, right boundary, and hit enter. So my maximum happens at 3.27 seconds and is a maximum height of 72.24 meters. So height is 72.24 meters, and it doesn't actually ask for the time on this one, so we don't have to actually do it. How long does it take for the ball to hit the ground? So again, that's going to be my x-intercept there. So I'm going second calc 0. I got to give it a left boundary. and a right boundary. And so x, which is our t, right? Because this is, again, this is t, this is h, which is really standard for these types of questions. T is 7.11 seconds when we round it to the nearest hundredth. And if it doesn't say what to round it to, hundredth is a really good call. Okay, so nothing crazy. The kind of regression thing is really the only thing that is new this year. Otherwise, I know you guys have seen this kind of stuff in different iterations, and it's just practicing different ones to make different equations. So go and do the snap practice and let me know if you have any questions. Okay.